Hey guys, Sebastian from Madrigal here. Welcome to part 8 of the video series where we create a Vulkan renderer for the Basis game engine. Today we're gonna start looking at the Buffer class. And the Buffer class is a little iffy in my opinion and experience. So writing a performant and well-behaving buffer class for a modern rendering API is maybe a little bit tricky, or maybe it's not tricky, maybe it's just that I don't know how to do it. But let's have a look at how I do it currently in Metal. So we have the buffer metal class, which derives from GFX API buffer, which this is essentially, this part is almost completely the same as we're gonna do with metal. We have some private things here. Actually, let's bring the we can bring in the implementation here. And I've written quite a lot of things here. You can pause the video if you want to read this, but in a nutshell, you can read and write to buffers by using this map functionality. And if you've used any other graphics API, you are probably aware of how mapping works. You call map on something. It returns a pointer to memory where you can write things. Mostly write. You can read as well in some cases, but mostly we're writing because we're uploading things to the GPU. And then when you call onMap, then it is essentially sent away, uploaded to the video memory or whatever. And the way I've done it with metal is that, first of all, we have something called a small buffer. So if something is a small buffer, let's quickly have a look and see where it is. So description size is smaller than this small buffer threshold, and I think that's like 4 kilobytes or something. It's pretty small, but anyway, if something is a small buffer, then we really don't create any video memory buffer inside this buffer metal at all. We just keep a CPU side buffer, and as you can see here, when you map things, you call map and it returns a pointer. It actually returns a pointer to the CPU side buffer. And CPU side buffers are, as you're well aware, I'm sure, you can just read and write easily to them. It's just any old buffer, really. And when you then bind one of those buffers, one of those small buffers to the pipeline, Metal has a way of just taking a CPU side buffer and just sending those bytes to the rendering context itself. You don't really need to create any, like reserve any video memory or anything like that. And I'm hoping that I'll actually be able to use something called push constants on Vulkan for this very thing. So small amounts of often changing data could just be used using a push constant. I haven't really looked into push constants. I know they're supported by VEC, but I'm not gonna try them out here. So we can just essentially leave out this small buffer logic for now. But then we have the other thing, the other sort of split here. So we have buffers that can be immutable, and if a buffer is immutable, let's go to create. Where's create? Here we go. So if we're not a small buffer, then we call CreateFrameBuffers. And here is CreateFrameBuffers. If this buffer is set through the buffer description that we give it, if we set the buffer to be immutable, we create one instance of the buffer and we upload the buffer to video memory. However, if it's not immutable, if it is mutable, if it is possible to write to this buffer, then we have to jump through some more hoops. Because we can't just allocate one buffer in video memory and just write to it over and over again. You can't like map a buffer and then write to it and then unmap it and then draw and then map again and expect all the draw commands to get their version of the data. That stuff works with APIs like D3, D11, but not really with the modern ones. So what I do here, and this may or may not be very smart, but what I do is, first of all, I have this small struct called Framebuffer. And this is not the same as a Framebuffer with a small b, like we just looked at previously. This is like a buffer storage struct for a particular frame. The name is a bit misleading, but that's what I used. So it's a buffer for a particular frame, and we have three of them, or we have essentially as many as this basis metal max frames in flight, which on the Vulkan case is basis VK max frames in flight. They're both defined as 3, right? We have it here actually. 3. So there can be 3 frames simultaneously being rendered to, and they each have their own buffer. So if you write every frame you write to a buffer, and then you draw a bunch of things with it, and then again the next frame you write something again, then it kind of makes sense that okay, each frame should have their own buffer, so that you don't actually write on top of something that's being currently rendered to blah blah blah. However, you can write to something multiple times during a frame, and that's why this actually has a vector of metal buffers called pages. And we have these two numbers here. We have a 64-bit unsigned integer, which keeps track of the last frame number when we wrote to this frame buffer. And we then have a size t, which keeps track of the last page index, so essentially index into this guy when we wrote. So the logic here is that if you write multiple times during a frame to a buffer, then the system will actually allocate more pages, so that you don't accidentally overwrite something that you may have outstanding draw calls using. You don't essentially step on your own toes, regardless of how often you write to the buffer. And yeah, this is probably not the most optimal way of doing things like this, but it kind of works. And I am going to pretty much copy this to the Vulkan backend for now, and I'll look into push constants and more effective buffer usage at a later date when I have something working. But yeah, this is a bit of a question mark for me. In the metal buffers case, whenever something gets bound to the pipeline, this GetBufferPage is called, and this returns a metal buffer. Don't worry about this ID thing. This is essentially what you get. You get like a pointer to a metal buffer. And so how does GetBufferPage work? Well, you can see here that, again, if we are an immutable buffer, and most buffers are, to be honest, so it's not as bad as it sounds. If you're an immutable buffer, you can just return the one and only frame buffer and the one and only page. Like, that's fine. If we're not, we need to figure out, okay, which frame buffer are we going to read from? So we ask the context which frame index we are on. This is actually a static member currently. So global data, yay. We get a frame buffer. And here, as the comment says, if the frame buffer was not written to when this buffer was last written to overall, it means the CPU side contains newer data that needs to be copied into the frame buffer. Right, so then we take this CPU side buffer always contains essentially the most recently written data. So we just copy it into the actual buffer that we want to use, and then we return that. It's not great, is it? Anyway, let's see if we can actually take all of this and make it work on Vulkan. And it should be slightly simpler because we don't have the small buffer logic there now. It might get even more complicated in the future. Not in this video series, but in the future. For me, because I want to use push constants. But yes, that remains to be seen. Right. So in any case, the nice thing with this whole ordeal is that VEC once again makes it quite easy for us to work with buffers, or at least that's what it looks like to me. So right, okay. VK Buffer is the thing that we will be using, VK Buffer. And here we can see. So buffers are represented by VK Buffer. We're calling VK CreateBuffer. It's actually VEC CreateBuffer. There's a typo there. And yeah, you have to specify the intended usage for buffer using the flag bits, blah blah blah. It selects essentially the right memory for you. It's quite nice in that sense. So, right, let's start with the struct because we know we're gonna want one of those again. So we want like the frame buffer thingy, and we want a vector of VK buffers in this case, and we'll call them pages. And then we want the uint, not 32 but 64 in this case. So frame number, and it was last write frame number. Yeah, and this particular part I have like the metal implementation here off screen for me as a reference, so I can just read some of those things off there. So last write page index. So again, this is the frame number during which this frame buffer was last written to, and this tells which index into this vector or this vector that value was written. Yeah, then we will want to probably have like void create frame buffers and void destroy frame buffers, and we'll want to have probably let's do createPage because that always requires a little bit of special handling. So let's abstract it away into or encapsulate it in a function. And I think I will want to actually use a function to do the writing. So write using map. All right. So we have the VK buffer. That's the page that we want to write to. We have the data. We have the size t size and size t offset. And the reason I'm actually making a function for this as well, right, using map, even though we have like map and unmap here, is that I will actually be copying memory into like newer pages, regardless of if we're actually using map and unmap, using this kind of method. You'll see in a bit what I mean. So render device VK. Device. Oh, I'm writing debug so often that I get lost. But yeah, the device, like we do with every class we implement, and then we'll want to have the CPU side buffer, and we'll want the last write frame number, which is like the frame number when any page of any frame buffer of this buffer VK was last written to. And then we have the frame buffers themselves, frame buffers, and this is basis VK max frames in flight. And yeah, let's do a memAlloc handle here, just because that was how I did it for the other one. You can use these kinds of handles to allocate memory a bit more easily, while still specifying the allocator that you need. You don't really need to worry about that. That's not terribly interesting. And then, just like you can get the buffer page from a metal buffer, we'll want to have the same kind of deal here. So GetBufferPage, and this is again, this will return the like a buffer page which is sort of ready to be bound to the pipeline without having to worry about stepping on anyone's toes. And maybe I'll do the same thing here too with the CPU side buffer. So let's just return that, get CPU side buffer, and I'll just return it like so. And I think I'll move this off to the side, and I'll open up the CPP here, and we can get started on the initialization. What is it complaining about? Oh, handle, right? Okay. So we have a device which we initialize to null. We have the CPU side buffer, which we initialize to null as well. We have mLast write frame number 0, and then the malloc, which we will initialize to mem allocator gfx API, like so. And in init, we will just essentially take the description and store it. I think that comes from, yeah, so that's stored in the base class. So that's cool. Debug name, yeah, we could implement debug names at some point. I'm not going to do them right now. Okay, so create. Well, first of all, we will want to create the CPU side buffer. That is used regardless of the type of buffer that we want to have. And if we have initial data, then we'll just do a mem copy into the CPU side buffer with the size and initial data, and again the size. So just copy that over, and then we can call the CreateFrameBuffers probably. I think that's it. And then let's do the opposite right away, because this is pretty easy stuff. So we can do alloc.free CPU side buffer, and we can null that as well, and then call release. Well, what did we call them? Destroy frame buffers is what we call them. Right. And that's it. Of course, there's more to it than that, but that's probably all we want in this case. And here we will indeed return the CPU side buffer. That is essentially the only thing we do, but it might be a pretty good idea to assert here that that the mdesc usage is GFX API dynamic. Trying to map a non-dynamic buffer, which I guess you could call static, but I don't really. A non-dynamic buffer tells you more than a static buffer. I don't know what a static buffer is, and and that's all that that mapping does. Unmapping is where the magic happens, as they say. So here we'll want to do FrameBuffer, FrameBuffers, and this is now maybe something that, yeah, we don't have the frame index. Some sort of typing based on the metal implementation here, but we don't actually have those indices in the render context VK, so we'll probably want to actually put them there. And let's just take them straight from the metal one. So metal, render context metal, and also the side. You can just actually I'll just move that off to the side. And I'll copy them here into the Vulkan one with the warnings and everything in comment form about them being global data and not that not being particularly good. And of course that needs to be VK. Right, so we have frame index, frame number, we initialize them to 0. That's it for now. We'll obviously have logic there to increment them, etc. But for now, this is good enough to get us continuing with the buffer logic. So last write frame number, if that is the render context VK's frame number. Then that means essentially that the buffer has been written to already this frame. And if fb.last write page index equals fb pages size -1, so essentially if it is the last one, then it means that all pages of this frame buffer have been written to during this frame. Allocate a new page, and here is where new page. Here's where this createPage comes into play. And initial data, well, that's just CPU side buffer. It's like that is the most recent data. So just use that. And we increment the last write page index, and then we actually just push the new page to the pages vector. Right, so in the else case, then there are 3 pages available. And again, we need to increment this guy, but we can just get VK buffer page is FB, FB pages FB last write page index. Not GB, but FB. How difficult can it be to write FB? And now we can use the write using map. So this is what I said earlier about this write using map function being pretty handy. Right. All right, and then in the else case, then we have the buffer has not been written to yet this frame. And in that case, we can simply reset the last write page index to 0 and indeed write to that page. So we just take this and write to it. And then we need to do the last write frame number, which is now, after we have written these things, now it's frame number. And also this buffer's last write frame number is also the same. So frame number, like this. Let's go through this one more time. So we get the frame buffer for the current frame. Oh, and I should perhaps mention that this frame index here, it goes from 0 to the max frames in flight -1. So it would be like 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2, etc. And this frame number just increases every frame, and that's why it's a 64-bit integer. So we don't get any overflow, or we won't get for like, I don't know, years. So this frame index would be that 0, 1, 2 looping number. So we get the frame buffer for the current frame. We check if we have already written to it this frame. And we check if we have written to the last one. If we have, we allocate a new page. Else we write to the most recent page. And if we haven't written to the buffer at all during this frame, then we just set the page index back to 0 and we write to the first index, which this will be 0 in that case. Then we update the number and we are done. So that's on map. Then we have this GetBufferPage. And this is where we want to check the description. If usage is immutable, then we just return FrameBuffers 0 pages 0, and that's it. That's all we do. We don't do anything else. But if it is not, then again we get the same frame buffer like we do here. And if the frame buffer last write frame number is not equal to the entire buffer's last write frame number, then that means that we need to update this particular frame buffer. So we set it to it. We set the frame buffer's last write frame number to the entire buffer's frame number. We set the page index to 0 again. And we do essentially this whole dance once again. And of course, if you don't continuously write to a buffer, then sooner or later this will become true, and we can skip this whole thing, and we can simply return the FB pages, FB last write page index, like so. And this GetBufferPage is the that's the function that gets called whenever the pipeline wants to bind this buffer. So this thing here and indeed this thing here, these are what actually then gets sort of forwarded to the graphics pipeline or compute pipeline, whatever you want to bind. Okay, so then we have the create frame buffers and destroy frame buffers. All of these private functions that we created here. Let's quickly lay them out. Shouldn't be that difficult. These are actually kind of the easy part. Like this logic here is kind of the tricky one. And of course, I'm not sure that this whole idea is the best it could be, but we'll see. Okay, so in the create frame buffers, once again, if we are immutable, then we can just create one buffer, and we want to make sure here that we actually have initial data. No, not that. Initial data is not supposed to be null. Trying to create immutable buffer without initial data, question mark. Like, that doesn't really make sense. Well, nothing can ever be written to an immutable buffer unless you give it initial data. So yeah. So don't do that. And again, it's initial data. And then we do frame buffers 0 pages pushback first page, and yeah, this guy last write page index is 0, and frame number is whatever it is, but it doesn't really matter because we're not really gonna use it. Anyway, that's immutable buffers. They are easy. Then we have a for loop iterating over all the three, or in this case, basis VK max frames in flight plus I VK buffer first page is VK null handle, I guess. Yep. And if we have initial data, then first page will be create page mdesc initial data, and we can set the frame buffers for I, last frame write number to the current frame number. However, if we don't have initial data, then we want to do something a little different. We can still use that actually, but to make it even more clear what we're doing, let's just give it NullPointer here. And here now we need to make sure that it's clear to everyone that this has never been written to. So we're going to do ff. That's 8. And we're going to copy it to get 16. And then write here that this fb has never been written to. So whenever someone tries to compare against this right frame number, they will go, oh, it doesn't match, I need to update the buffer, and then that's it. That causes it to be updated properly. And I think we can take these like so. And then of course we want to update the whole buffers, the entire buffers. Render context VK, frame, not frame index, but frame number. Yeah, I wouldn't be surprised if I had accidentally used frame index somewhere when I should be used frame number, or vice versa. Sounds like something I would do, to be honest. Okay. This looks pretty good. This looks pretty good. I think this will be quite good. Let's build it and see if it builds. It does not build. Okay. Yeah. Okay. We haven't gotten to the CreatePage function yet. It's here. But we'll get to it right after we release the frame buffers. So once again, let's copy this if here, and we can just do VEC destroy buffer, right? VEC, yeah, yes, destroy buffer, indeed, because we're going to be using VEC create buffer later on to create them. So this is the opposite. Frame buffer 0, pages 0. That's it. And yeah, I guess we can do this thing to clear. So then we have another one of these for loops for the other case where we don't have just one immutable buffer page. So we have frames in flight, but we actually need to iterate over the pages as well. So I guess for a vector, the correct data type is size t. Call this j, and we'll call this mFrameBuffers I dot pages dot size, and then we have something a little similar but not quite. So that would be I, and this would be I, and that would be j. Right, so we run through all the three, in this case, frame buffers, and then we iterate over all the pages, and we destroy all the buffers, and then we clear the thing. Cool, that should be it. I think that's all we need to do for destruction in the entirety of this buffer thingy. Okay, so let's do CreatePage last because it's the most complicated one. We can do it right using map, and right using map actually uses actual VEC mapping functionality. Yeah, I'm not sure if that is. I think that might actually be the only way to write to a buffer currently in VEC. With the textures, we use this VEC image subdata, which I think uses buffers underneath under the hood, so to speak, and updates image data with this. Maybe there's something we can do with buffers, but we're using map for the time being. Okay, so VK result, come on, result is actually, before we even do that, we want a void pointer. So P is NullPointer, right? And then we want to do VEC map buffer. Yes. We want the device, as always. And we want the page, which we give in. We want the offset, I would assume. Yes. And then we want the size, in that order, apparently. And then address of P. And then we do a memcopy into P. Destination size is size, source is data, and source size is also size. And yeah, then we need to do something. Actually, let's do the VEC unmap buffer. And I had here in my notes something that I read. Let's just make sure that actually returns a void, so we don't actually do any result thingies. But here we can do a basis assert if that result equals VK success. Oh, not suboptimal. Not suboptimal anything. So VEC map buffer failed. Result %d. Yeah. Assert if. Right. Yeah, and this still doesn't return anything, so let's just make it return VK null handle for now, just so that we can actually build this, compile it, and make sure that we don't have any other issues. Make a comment there for ourselves. Right, so yeah, something that I read in the VEC documentation here is to map and unmap a buffer, an application calls VEC map buffer and VEC unmap buffer. Care must be taken to call VEC flushed mapped buffer ranges to guarantee writes by the host are visible to the device. The behavior remains nearly identical to Vulkan's VK map memory, blah blah blah. And looking at the VEC samples, we actually want to call this function between the mapping and unmapping. So let's do that. And this guy actually wants, what was it? VEC mapped buffer range. Yeah. Yes, indeed. So buffer range, initialize it like that, and call buffer range dot. Okay, so the buffer is, that's page. Buffer range is offset is 0, and size would be, we can use size, or we can use this magical whole size macro, which specifies that we want the whole size. Yeah, all of this I read from the VEC documentation, by the way. So if you're wondering where I got those details, they're all in there. If you want to have a look, get VK device, buffer range count. Okay, well that would be 1, and then address of buffer range, something like that. Okay, and I think that should be right using a map completed. We still need to create page, obviously, this guy, and it is actually going to be slightly more complicated, I fear, but never fear. I wonder about this offset. Like, should we? We're mapping it here. We're flushing the whole thing, even if we're writing. Yeah, this probably works. I'm gonna leave it as it is for now. it may of course be that yeah. Well, that should be fine. Okay, even if you have an offset here, this P will be valid. Yeah. Yeah, I think this offset is actually I don't know, maybe this should be offset, but I'm gonna leave it as it is for now. That's probably the safest way to do it. Like it's flushing the whole buffer. From beginning offset 0 and onto the end with the whole size macro. Yeah. The validation layers should shout at us if we're doing something stupid once again. Okay, so last thing for today, last thing for this this part of the series, we're gonna create the page. So page handle, is VK null handle. Almost everything that we create in VEC or Vulkan is through this like passing like an address to something that's. So I assume like the VEC CreateBuffer is going to work the same way. And we'll want to fill in like a VEC buffer create info, buffer create info, and initialize it like this. Okay, and we'll do size is mdesk.size. That's null. That's family indices. I think those can just be null, can't they? I think so. Let's have a look here. All right, so we give the size and then the usage. Those two we have to give. Okay. Okay. Oh boy. What is usage? What is it? It's VK buffer usage flags. Okay. Okay. Usage and VK buffer usage. Transfer source destination bit probably. Okay, if we want to map it, I would assume. But let's switch on the disk dot type, right? I think this one we can have Visual Studio generate these guys for us. Yeah, okay, so usage, I think there are actually flags for this. So this would be VK buffer usage. I saw a vertex something there a moment ago, yes. that looks good, and maybe there is an index buffer as well. There seems to be. Whoa, 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 whoa. And what would this be called then? Let's just look at it here. Right, so we have transfer destination bit. That's good. Uniform texel buffer, storage texel. Probably uniform buffer is the one that matches the constant buffer type. And storage buffer is the one that matches the structured buffer type. Right, something like that. I don't know what these texel ones are. Let's hope I don't need them. But again, it should be, the validation layers should shout if we do something stupid. Okay. Then is that actually all we need? Maybe that's all we need. VK result, and this would be like VEC CreateBuffer, maybe? No? Yes. Oh, there we go. Buffer and mem flags. Oh, VEC memory flags. Okay. VEC memory flags. Yes. Come on. Okay. Yeah. Yeah. These are the ones that aren't actually. These are not available in native Vulkan. Because these are kind of higher level than what Vulkan would give you. So here we can do this. We can do CPU access, and we can again ask Visual Studio to expand that for us. So yeah, we don't want map write no overwrite here because that's not really applicable. But we want these three. So we want read only. Read only would be as memory GPU to CPU, right? Yeah, those are flags, okay. And write only would be mem flags is that would be, come on, give me that one single word. That would be CPU to GPU. And then we have this case here, which would probably combine them two, right? Both read and write. It's not that common, but I guess it might happen. So GPU to CPU and CPU to GPU. So just make sure I have those correct. Yeah, I think that's probably enough for now. This covers almost all the cases. And so I think that's what we'll do. That's what we'll do. I wonder, maybe we could actually write no overwrite. I wonder if that should be like CPU to GPU. I mean, this is like a D3, D11 trick that I don't really use. Maybe that is the more correct way to do it, so to speak. Yeah, I don't know. I'm not sure. Let's leave it as that. That's probably fine. And then m device vk get vk device. Memory flags is memory flags, and that would be the address of, what did we call it? Buffer create info. And then the page handle, like so. And we'll copy one of these guys from over there and copy it there. And Right, so then we still need to actually do something with this initial data. And I started thinking about this GPU only flag. Like, this is probably not mappable, right? So if mem flags is indeed as memory GPU only, then we can't map it, right? I think there was actually a mention of it here somewhere. Yeah, the VEC memory GPU only is the only enumeration value which cannot be mapped. So maybe there is like a sub-data function for buffers as well. Do we have like VEC buffer sub data? Okay. Okay. All right, that's nice. Okay. Okay, good. I don't know. Maybe I should use this for more than just this thing. But, whatever. Let's just get this working first, and then see if I should switch some of these things around. So page handle offset is 0, size is like mdesk size. Data is initial data. There we go. Yeah, that should be it. And if we don't use GPU only memory, then we should be able to use this guy. Hello. Page handle, initial data, size is desk.size, and offset is 0. Okay. Right. So that should be basically it for the buffer, finally. This was a pretty long and work-heavy thing to put together, and we're over 250 lines of code, so it got pretty long in the end. And now, oh, what do we have? We need to return something. We need to return something. What do we return? We return the page handle, don't we? Like that. But now if we return this, we should crash in a completely new place, which is always exciting. Yeah. This was NullPointer. What? 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 Oh. What? That's weird. GFX API object. Like, is the... What? What is going on? Create page. So device VK is null. Okay, do we not set it? We don't set it. We set it to null. That's stupid. I should set it to device. Yeah. Okay, that was my bad. Yeah. I'm getting tired. It's been a long day. Yes. Oh boy, we get actually like a window now. Oh, hey. Do you guys realize what this means? This means that we'll probably enter the main loop of the game. So let's go to, like, I don't know, main menu state in slide, and see if we hit update. Yay, we do. So we're we've gone past the renderer setup now. And we're now actually looking at the... Oh, shit. Oh, boy. Okay. Okay, that's not good. But here we can see this is an example of what a validation error looks like. As you can see, validation error is not a warning, and it gives us some hints about what went wrong. Number of currently valid memory objects is not less than the maximum allowed, 4096. That's not good. But yeah, one thing at a time, one thing at a time. Yeah, I don't know why we ran into that. Let's see if does it happen again if we just run it again. Or was it something about me? I don't know what I did. I resized the window a little bit. I guess that might trigger it as well. Of course, we're not actually we're not asking Vulkan to do any work here. Oh shit! Oh no! Look at the look at the memory going up. Oh, something is wrong. Something's definitely wrong. Yeah, that's not great. Using 8 GB in the main menu. That's interesting. Okay, well. Yeah, okay, we get the same thing again. Alright, that's interesting. I wonder how much memory does like the average build of the game use in the main menu. How old is this build? It's from August. Now we can just quickly have a look here and see. So yeah, it's sitting at around 300 megabytes, which is obviously closer to what we would expect. But yeah, there's something funky going on there, but I will have time to actually check that out. It's not that big of a deal. Anyway, we got into the main loop this time, so pretty cool. We actually got past the setup phase. It's no longer crashing on any invalid objects or anything. So that's very nice. That is very nice. Cool. Next time I think we'll actually start probably looking at shaders and pipelines. So we have shaders, pipelines, the render context, and samplers left. And samplers and shaders should be pretty simple. The render context and the pipeline should be pretty tricky. So maybe we'll tackle like shaders and samplers, both of them in the next part, and then slowly but surely we can actually start rendering things. So that'll be fun. Okay, I'm gonna end this now. You know what to do. See you in the next part. Bye.